what is this phase transformation is. So this phase transformation and the heat treatment are, they are kind of interconnected topics. The development of a set of desirable mechanical properties for a material often results from a phase transformation, which is wrought by a heat treatment, right? Set of desirable mechanical properties. So heat treatment is purposefully for desirable mechanical properties. Maybe in some materials we will have the desired properties, some materials we would not have the desired properties, right? So we want those materials to achieve those properties, right? So for that purpose we go for heat treatment. So say for example iron, if we want it soft then we will go for annealing. If we want it hard then we go for quenching or hardening, right? So desirable mechanical properties we can achieve through this heat treatment, right? It often results phase transformation, which is brought by a heat treatment, right? The time and temperature dependencies of some phase transformations are conveniently represented on modified phase diagrams. So I told you this time and temperature are the two key factors while designing this heat treatment process, right? So for which treatment, which heat we heat up to, and up to what time we leave it, right? So these are the two main parameters. It is important to know how to use these diagrams in order to design a heat treatment for some alloy that will yield the desired room temperature mechanical properties. So we have heat treatment diagram, right? Or we call it as, for now our purpose, we are going to use only iron and carbon, right? So that can be called as iron carbide diagram also, right? So which is the uh, basic understanding diagram for any alloy to mate, right? So I told you most of the metals have different phases, alpha, beta, gamma, delta. There are different phases, right? So these phases dependent on up to which temperature we heat them and up to what's the solubility in the other alloys on this, not alloys, sorry, other materials inside, right? So in that case, we have this iron carbide diagram as the basic structure to understand this phenomena, what is happening. It is important to use how to use these diagrams, right? So these diagrams, right, these diagrams mean iron carbide diagram, which is coming in the next slide. These diagrams are the basic structures to understand what is happening, I mean which temperature what is happening, at what time which is happening, on which structure it is being there, whether it's BCC or FCC or what structure is it there, right? So these questions can be answered just by looking at these diagrams. In order to design a heat treatment for some alloys, so here we are providing only for iron carbide, that's an example. So any material you are mixing, you can form a diagram like that, right? Will yield the desired room temperature mechanical properties, right? Yield the desired room temperature mechanical properties. The tensile strength of an iron carbon alloy of Eutectoid composition, you don't not worry about this word, I will explain, can be varied between 700 MPa and 2000 MPa depending on the heat treatment employed, right? 700 to 2000 MPa megapascal depending on the heat treatment employed. So how we do this heat treatment, it can vary, right? We will see what is this Eutectoid and what's special with this 0.76 weight percent. Okay, we will see it in the next slide, right? Right, this is your diagram. It is called as iron carbide phase diagram, or shortly we call it as iron carbide diagram. All right, so this diagram shows you here you see some temperatures, right? Temperatures. Here you see some compositions, right? Composition is weight of the other alloying element, right? And there we have another diagram which is called a stability diagram. There we have the time also, right? So those diagrams will provide you clear understanding of when we are going to any kind of heat treatment process. You just can't just randomly heat to a temperature and add alloys, right? You need to be specific. We will see why, right? So now you see this diagram, right? So there are some temperatures, particular temperatures you see here: 1538, 1493, 1394, right? here 912, then here 727, right? These are some specific temperatures. Also here in this blue cages you see 0.022, right? This is composition, that is percentage addition. So here this point is 0.022, this point is 0.76, this point is 2.14, here 4.3, and here 6.7, right? So these blue cages are the addition of carbon, right? Addition of composition weight percentage of carbon. So for 100% of steel, how much of percentage of carbon can solve in that iron, right? How much percentage of carbon can solve in this iron? When we were talking about this sugar lime juice, you remember, right? So only a certain amount can solve. We can't impose more, right? So in these particular temperatures, that would be the maximum solubility. All right. Now we will see one by one. Okay. This region, right? This region here you see that is alpha ferrite, right? That is alpha ferrite. So this region I am talking about. All right. This is right. Okay. I will color it by red. Right? This particular region, this is alpha ferrite. In alpha ferrite structure, all right, in 727 degrees Celsius, the maximum solubility of carbon is 0.022. Okay. Yeah, and carbon diagram in 727 degrees Celsius. Okay, the explanations are there. As you see here, ferrite can accommodate 0.022% of carbon at 727 degree Celsius, right? So here the alpha ferrite can accommodate 0.022% of carbon at this 727 degree Celsius. Okay. And when you heat it further, right? So here is your temperature. Okay. When you heat it further at 912 degrees Celsius, right? 912 degrees Celsius, it is changing to gamma Fe, that is austenite, right? So alpha Fe is called as ferrite, gamma Fe is called as austenite, right? At 912 degrees Celsius, this alpha is turning into gamma, right? So alpha is turning into gamma means the structure is completely differing. So here in the alpha, that is of BCC structure, right? While in the alpha, that is changing to FCC structure. You see here. So ferrite alpha Fe, pure Fe, room temperature 912 degrees Celsius. A single phase BCC solid solution, right? So up to 912 degrees Celsius, this is alpha ferrite, and which is of BCC structure, that is body centered cubic structure. When it go to austenite, that takes the form of FCC, that is FCC face centered cubic structure. So you don't need to panic why this is called as ferrite and why that is called as austenite, because of this region. Here it is of BCC structure, okay, but here it is of FCC structure, right, which is called as alpha Fe or austenite. Okay, in this phase, right, in austenite phase, at 1147 degrees Celsius, okay, 1147 degrees Celsius, carbon has the solubility of 2.14%, right? The composition of weight percent of carbon is 2.14%, right? This is the solubility, maximum solubility. All right. So that is here. You see, ability to be deformed and to absorb carbon up to 2.14% at 1147 degrees Celsius, right? So this is at austenite, that is gamma Fe. A single phase FCC solid solution alpha ferrite transformed from BCC to FCC at 912, right? So here it was of BCC up to 912 degrees Celsius. It was in the form of body centered cubic. When it go passing this 912, it is turning to FCC, that is face centered cubic. All right, and that is called as gamma or austenite. And 2.14% of carbon can mix into this. All right. Now we have enough cementite, that is Fe3C, right? Fe3C is called as cementite, right? This region, this shaded region is the alpha Fe. So what about this region, right? What about this whole region? So this region has alpha plus Fe3C. Why? Because we have 6.7 Fe3C. So here cementite is Fe3C. So this complete line is the composition of, you see, weight percentage of carbon, that is Fe3C, not Fe3C actually. This is composition of carbon added, right? So when this Fe3C and this alpha are mixing, this region is completely filled up with alpha plus Fe3C, right? So here you have alpha Fe, here you have Fe3C. So in between, this region is completely filled with alpha plus Fe3C. All right. Now again, this region, okay, I'm talking about this region. I will shade, right? So this region I am talking now, okay. It is known as, mentioned as, you see, alpha plus gamma, right? So what's happening here is this particular region is alpha, right? You know, this particular region is alpha, that is BCC Fe structure. This region is gamma, that is FCC ferrite structure, right? In between these two, as like here, we have the mixture of both alpha and gamma, right? So this is not complex, right? So this region is alpha, this region is gamma. So in between this region, there is alpha plus gamma. So similar thing here, alpha, gamma. So this region would be of alpha plus gamma Fe. So here in this particular region, we will have both BCC structure as well as FCC structure, right? BCC as well as FCC structure. So these X and Y and Z are mentioned, that we will look at later. So these are indicating the structure, I mean the atomic structure. How will it look like if you go into micro view, right? That we will see later. So you don't need to panic about this one now. So now we will complete all these phases and temperatures, right? So here the gamma austenite, and this is alpha plus gamma. All right. Now again, here we have Fe3C. This region we have gamma, that is austenite. So this region, which is in between gamma austenite, gamma Fe, that is austenite, and Fe3C, will have the mixture of this and this. You see, gamma austenite is here, Fe3C is here, right? So whatever the constituent forming in between two formats, right? So here we have Fe gamma, here we have Fe3C. So the region in between these two will form a gamma plus Fe3C region, right? Gamma plus Fe3C region. And now here, at this particular point, at 727 degrees Celsius, all right, gamma austenite will have 0.76% of carbon maximum it can mixed into, right? So here at the 727 degrees Celsius, while it is in BCC structure, the mixture, I mean solubility is 0.022%. But when it comes to gamma, the solubility is increased at the same temperature. You see here also that is 727, here also that is 727. At the same temperature, the solubility increased to 0.76 degree, not degree, 0.676%, right? So this is what I asked you when about the heating. So when changing the structure from BCC to FCC, the solubility increases. At the same time, when increasing the temperature this way, also you see solubility increases. So here it's 0.2 and 0.7, but here it is 2.1 and 4.3. You see, so when the temperature increases, the solubility also increases. Similarly, when changing the structure also, solubility varies, right? From BCC to FCC, again solubility increasing. All right. So this is 0.76 and 727 degree things. All right. The temperature is 1147. Okay, 1147. So in 1147, the solubility of gamma, solubility of carbon with gamma Fe, that is austenite, is 2.14 percentage, right? But when it comes to liquid solution, you see here that is liquid. When it comes to liquid, the solubility is increasing to 4.3 percentage, right? 4.3 percentage. All right. Again, here we have the liquid phase. You see L means liquid. Okay, liquid means it's completely melted. So you know the melting point is around 1538. So this is completely melted. So the region here is austenite, region here is liquid. So as I told you, the region in between will form the mixture of this and this, right? So that means liquid plus gamma, right? Liquid plus gamma. All right. So this side we have gamma, here we have liquid. So the phase or region formed in between this region will be the mixture of these two, right? That is liquid and gamma. All right. Similarly, here we have Fe3C, here we have liquid. So the region formed in between will have the mixture of these two, that is liquid plus Fe3C, that is cementite or and carbide. All right. So these are the structures here in this region. Okay. E point I already explained about, and now we see this delta point. You see here, you see this delta. Okay, this region, right? This region, this small region is the delta Fe, right? Delta Fe. So that is formed in the region of 1394. So from austenite, that is gamma Fe, to delta Fe, it is changing its phase at the temperature of 1394, that is 1394 degrees Celsius. Here this structure, right, this structure is again BCC. Okay, so here the phase is transferring. So from FCC, right, from FCC it is turning to BCC again at 1394 degree Celsius, right, 1394 degrees Celsius. So now we have delta Fe here, austenite here. So this region, right, this region, this small region in between this will be filled up of mixture of this delta and gamma, right? So the region I am talking about is this yellow shaded region. Okay, this region will be filled up of gamma and delta, right? Gamma and delta, because this is in between these two. All right. Similar way, this region, right? So I will need another color, right? This region is between L, that is liquid, and gamma. No, not gamma, delta, right? So this will be mixture of L plus delta. All right, L plus delta. In the similar way, we have another phase change here, right, at 1493. So this, and here we have one, and here we have one. These three changes, right? This change, and this change, we have special characteristics. Okay, that we will study in the next to next slides. Okay, so this is how this phase diagram is arranged. So here you see at particular temperature ranges, particular amount of carbon can mix. Okay, so this diagram is called as iron carbide diagram. So whatever the alloys you are making, say for example you are making aluminium and some pro X another alloy, and similar way you can draw diagram. That diagram will, these temperatures will be vary, the amounts will be vary, but it will take a kind of similar diagram. Similar means it will not exactly similar. Since it has three phases, we have this big diagram, right? Three phases in the sense alpha Fe is here, gamma Fe is here, delta Fe is here. That is three phases we have. So that's why we have significant three regions, 1, 2, and significant three regions. Maybe if it does not have a third region, we would have only up to this much. So within this, we will have some other arrangements, right? So that based on different metals, right? Their individual characteristics. From here, you can identify how much maximum alloying you can go for, right? So here, you know, if it is 727 degrees Celsius, by this diagram, you know the Fe will be of BCC structure. So in that BCC structure, only 0.022 can solve, right? That's a conclusion you can derive from here. Also, you can think that if we increase the temperature, that will turn as austenite. So austenite will have 0.76% of carbon solubility at the same temperature, right? So same temperature is starting from here. So throughout this range, it can have this 0.76 percentage of solubility, right? So particular degree Celsius, right? In particular temperatures, how much mixture can mix as alloy specifically can be determined from this iron carbide diagram. All right. So this way it is given as degree Celsius, and here it is given as Fahrenheit. Okay, 1500. This is Fahrenheit, and here it is Celsius. Okay, and this region it is percentage. Here in this diagram, what you need to have in mind is this particular composition value, that is 0.022, 0.76, 2.14, 4.3, and 6.7. So these values you may have to have in mind. Also 727, 912, 1147, 1394, 1493, and 1538. These temperature values also you need to have in mind, right? Second thing. Third thing, on which regions, which forms or phases exist, right? So here alpha, here gamma, here delta, here mixture of gamma plus liquid, here mixture of gamma plus Fe3C. This composition also you need to have in mind, right? Important phases in the iron carbide system. Thermal processing or heat treating. So this is what we have studied now. The art and science of controlling thermal energy, right? Art and science of controlling thermal energy for the purpose of altering the properties of metals and alloys. So I told you, in order to attain desired properties, we go for heat treatment, right? Heat treatment. Ferrite. So alpha Fe is called as ferrite. Pure Fe, room temperature to 912 C, a single phase BCC solid solution. So this I showed in the diagram. Up to 912 degrees Celsius, it will remain as alpha Fe with the structure of BCC. All right. Ferrite can accommodate 0.022 carbon at 727 degrees Celsius. Right. So that's why I told you these temperatures and these values are important, right? Then austenite. Austenite is gamma Fe. All right. Gamma Fe. A single phase FCC solid solution. Alpha ferrite transform from BCC to FCC at 912. Right. So again here single phase FCC solid solution. So austenite, I show you this region, right? This region. it is FCC and single phase. So why we are saying single phase is in this region only austenite is there. Okay, in this region only alpha, that is ferrite, is there. Okay, here in this region only delta is there. So these are the single phase regions, but in all the other regions they are mixtures. See, A plus B, A plus B, A plus B, right? They are mixtures, right? So that's why it's mentioned single phase, right? So that's why it's mentioned single phase FCC solid solution, which will transform from BCC to FCC. When it coming from alpha to gamma, that transformation is BCC to FCC. That will occur at 912 degrees Celsius. Characteristics: ability to be deformed and to absorb carbon up to 2.14 at 1147 degrees Celsius. So at 1147 degrees Celsius, it can absorb 2.14% of carbon. But which one? Austenite, right? So austenite can absorb 2.14% of carbon at 1147 degree Celsius. All right. Then we have cementite, right? Cementite or iron carbide, we call it as Fe3C, right? So this Fe3C intermediate phase with the chemical formula Fe3C, right? So chemical formula is Fe3C. So this line represents this Fe3C. You see here Fe3C, right? 6.7% carbon, brittle and hard, right? So here you see that is 6.7% carbon added with Fe, and it is hard and brittle, right? Hard and brittle. So I told you if the hardness increases, then the brittleness will also increase. So this is hard and brittle. Right, now you see these two words, Eutectic and Eutectoid, right? So when I show these words in the previous slides, I told you about this one, not to worry. So now we will see what is this Eutectic and Eutectoid, right? These are just two terms. One eutectic reaction exists for the iron-iron carbide system at 4.3 weight% carbon and 1147 degree Celsius, right? Line PEG. Okay, line PEG. All right. So this reaction occurs at 1147 degree Celsius and at E point, right? E point, right? So this region, this reaction is going to occur. There you see L 4.3 weight% of carbon, right? L is liquid iron solution, 4.3 weight% of carbon, right? So you see here liquid iron of 4.3 weight% of carbon. So this is that region. Will turn to, right? That will turn to gamma 2.14 and Fe3C, right? Gamma 2.14 and Fe3C, that we will see here, right? This gamma 2.14 and Fe3C 6.7, right? This is L 4.3. This line we are now talking about. All right, the transformation occurring along this line, okay, not this way or this way, along this line, this way the transformation is occurring. Liquid iron of having 4.3% of carbon, right? So here at this point, right, at this point, what is happening? We are looking towards this. We are looking by this reaction, okay? So slightly above this point, somewhere here, the component is liquid carbon 4.3%, right? Liquid iron with carbon 4.3%. Slightly below this point, right? What is the constituency here? Gamma plus Fe3C. Right? So when coming along from here to here through this particular line, not line, point, we will have these two components, alpha plus Fe3C. So not alpha, gamma plus Fe3C. Along this line, through this point only, gamma, right? Gamma you see here, that is 2.14% mixture, right? Similarly, Fe3C, that is cementite, that is 6.7% mixture. So that's the two borders, right? For this reaction, right? For this reaction, at this point in this line, G and P are the two borders, right? So when it coming from here to here, there I have liquid, here I have gamma plus Fe3C, right? So this gamma, how much percentage, which can be determined from here, that is 2.14 percentage. Similarly, this Fe3C, right? Fe3C in this line, that is 6.7%. Okay, and this particular point, this liquid forms, liquid can accommodate 4.3 percentage of carbon. All right. So this is what called as this eutectic reaction, right? Eutectic reaction. So you see here, eutectic reaction, eutectic, and the difference is here eutectoid, right? So this is the difference, eutectic and eutectoid. All right. So this reaction occurs along the line, along this line. Okay. What do you think will happen if this reaction, right, along this line, if this reaction, if it is shifted somewhere here, and if it is occurred like this, what do you think will happen? Or if it is shifted to this way, right, and if it is occurring like this, what do you think will happen? Why we are looking the reaction along this particular region? Why is that? So here there is a particular point, right? So if the reaction is occurring through this particular point, actually the phase transformation is from this region to this region. Okay, this is a phase transformation. But if the reaction occurred along this line, right, the phase transformation is not from this area to this area, but it undergoes another region, this one also. All right. Similar case for here also, the transformation is not from directly from here to here, right, but it is undergoing in another region which has the mixture of this and this, right? It has a mixture of liquid and gamma. Similar way, this has a mixture of liquid and Fe3C, right? So that may affect or accommodate some extra forms or phase, right? So in order to remove that, or we don't want that ingredients, that's why we go particularly to do through these points, right? So that's why I told you these temperatures and compositions are very important while drawing this diagram. But if even if there is a 0.1 weight composition difference, so between 4.31, which means that is in this region, right? It is 4.29, that is in this region. So anyhow, that is going to accommodate some parts from here, right? Some parts from here, but we do not need this, right? So that way particularly we are going through this region, right, through this point. All right. So there we can obtain exact phase transformation from this region to this region. No any disturbance due to these regions. All right. So if it is go through this region, you need to consider this L region, this gamma plus L region, and this gamma plus Fe3 region. So whatever the regions it is covering, you need to consider. So this will be a kind of metastable state, and this will incorporate some parts or components from this region also. So we will see about the next reaction. There is one Eutectoid reaction exists for the iron-iron carbide system at 0.76 weight percent carbon and 727 degrees Celsius. Line NOH. Okay, we'll see where is this NOH is. NOH, right? This line we are now talking about. So his line, this X part only we will be considering. Okay, X part only we will be considering. So we'll write the reaction. That is gamma 0.76 is turning into, right? So there is gamma 0.76, right? I will write that one. Gamma is here. I will write 0.76. This is turning into alpha plus alpha Fe3C, right? Alpha plus alpha Fe3C. Alpha plus Fe3C. So here this is 0.022 and here it is 6.7. All right. Here it is 0.022 and here it is 6.7, right? So this alpha 0.022 and Fe3C 6.7. So we will see about this reaction. So when you cool down from anywhere in this temperature, right? Anywhere in this temperature. So you remember the heat treatment. So there once it's mentioned 700 to 800 degrees C, right? That is not 700 actually. That must be above 727. Then only it will be in this phase, right? Then only it will be in this phase. So here you can go any temperature up to, doesn't matter. But why are we going to waste heat energy here? If it is coming at to FCC structure after 727, we may stop with 750 somewhere here, right? Whether it's 750 also, this will have the FCC structure. But if it is 1250 also, this will have the same structure, right? So we don't need to waste that much energy while heating, right? So we will stop somewhere here, 700 to 800. That's why it is mentioned as 700 to 800 degrees Celsius. You can go on while you are doing this heat treatment. Okay. Now what is happening along this line X? Okay. Now the reaction what I am talking is happening along this line X, which is passing through this O. Here the gamma austenite, right? So you see gamma at this point has 0.76% of carbon, right? At this temperature, gamma has 0.76% of carbon. It is turning as alpha plus Fe3C, right? Alpha plus Fe3C. This alpha is 0.022%. You see here along this line, right? We are talking about along this line. So in this line, right? In this line, we have one boundary here, this point that is 0.022, and another boundary here that is 6.7. All right. So this is 0.022 and 6.7. So these are the two boundaries, right? So gamma, that is austenite state of Fe, having 0.76% of carbon, right, slightly above this point, is turning as slightly below this point. What is it turning as? Alpha having 0.022% of carbon, not carbon, alpha ferrite, and Fe3C of 6.7%, right? So this reaction is called as Eutectoid reaction. Okay. So the way reaction is happening is same. It is happening from here to here in this diagram, here to here in this diagram, along this point in this diagram, along this point in this diagram. Here we will have both the borders, this border and this border, P and G for this reaction. Similarly, we will have N and H, two border constituents, not constitution, constituents for this reaction. All right. So this Y and Z are mentioned here. So what I explained here will be applicable for here also. If it is passing through Z way from gamma austenite, it will take this format, that is gamma plus Fe3 form, and then it will take alpha plus Fe3C form, right? Or if it pass through Y, it will start with gamma form, then it will pass to alpha plus gamma form, then it will come to alpha plus Fe3C form. What is the difference between two reactions? Okay, so here the constituent addition of carbon is 0.76. Okay, but here that is 4.3. First thing. And here the temperature is 1147. Here that is 727. Also here the phase transformation is from FCC to BCC. Here you see liquid to FCC, right? So these two reactions are not the same. Mainly the ingredient is different, the carbon content is different. So if I want to say rough, it is producing different type of steel. Say for example, if it is producing mild steel, this can be considered as hard steel. That I'm saying for example. So this increase in the carbon content is having like a great influence on the strength. Okay, so you don't just see this is on only 3% increase, right? So we don't put like 30% increase. So this small increase in the carbon have very high impact on the strength of the steel. Okay, so that's what I'm saying. So this reaction, it is 0.76 carbon addition. Here that is 4.3, and here the temperature is low. Here the temperature is high. All right. So these are the differences between these two reactions. So one Eutectoid reaction exists for the iron-iron carbide system at 0.76 weight carbon and 727 degrees Celsius. This gamma Fe turning as alpha plus Fe3C. Yeah, so here I have like some further written description about these things. Phase in Fe3C phase diagram, right? Iron carbide phase diagram, right? So this is some statement about alpha ferrite, right? Alpha, which is called as ferrite, solid solution of C in BCC Fe, right? Carbon in BCC structure. Stable form of iron at room temperature. Okay, this is stable form of iron at room temperature. Because if you see the temperature range, right? If you see the temperature range, it is somewhere here, right? So that is stable at the room temperature. Maximum solubility of C is 0.022, that we have already seen. Transforms to FCC at 912, right? So this also we have already seen. It will transform from BCC to FCC at 912 degrees Celsius. And then I have gamma, which is austenite. So here the maximum solubility of carbon is 2.1 for this we have already seen. Transforms to BCC to delta ferrite at 1395. So BCC to delta at 1395. It is not stable below the eutectic temperature 727 unless cooled rapidly, right? So you see this temperature 727. It is not stable below this temperature unless cooled rapidly. So below this temperature, it is not stable unless you cooled it rapidly. Delta ferrite solid solution of C in BCC Fe. So again now here BCC, here FCC, again here BCC. Okay. The same structure as alpha ferrite. So alpha ferrite and delta ferrite have same structure BCC. Stable only at high temperature above 1394, right? And melt at 1538. So you see here at 1538, it will melt and form liquid, right? Form liquid. Also, the phase starting from 1394, right? So this state is applicable only at like from this to this temperature, that is around 140, right? The difference between this and this around 140 only, 140 degrees Celsius only, it will be in this delta form. Okay, this is stable only at high temperature above 1394, right? This is about delta Fe. Then I have Fe3C, that is iron carbide or cementite, both the way you can call. This intermetallic compound is metastable. I told you what is metastable is. It remains as a compound indefinitely at room temperature, but decomposes very slowly within several years. You see, several years into alpha Fe and C, graphite, at this temperature. Okay, so this will remain as iron carbide. This does not have any problem.